Today we're going to be discussing the basics of chemistry. Metals, and we're going to start by distinguishing what metals and nonmetals are. Metals are typically a hard and shiny substance which is solid at room temperature. They're also denser than other elements and they're usually opaque. Nonmetals are the complete opposite of metals and lack physical and chemical similarities between them. They also differ in physical and chemical properties such as their conduction of heat and electricity. Physical and chemical properties of metals. Some of the physical properties is that they're ductile, which is why they're used in wires. They're malleable, which is why you see iron in many different shapes and forms. They're dense, they're shiny and lustrous, which is why they're used in jewelry. They're hard, which is why they're used in bridges and statues. They are sonorous, which means that they make a sound when they're hit because their particles are so tightly packed together. Some of the chemical properties is that they're good conductors of heat, which is why they're used in pots and pans. They're good conductors of electricity, which is why they're used in wires. They react with nonmetals to create ionic compounds. Because they have a strong metallic bond, they have a high melting and boiling points. They also form an alloy, which is a harder substance created from two metals. They're solid at room temperature with the exception of mercury, which is found in a liquid state. They corrode when reacted with air. They produce an oxide when reacted with oxygen. The reactive metals are stored in oil, while the non-reactive metals, such as gold and silver, are used in jewelry. And they have a low electronegativity. How can you find them? The metals are located in the middle of the periodic table and the left of the periodic table. The ones in the middle are just called the transition elements. All of the blue elements here are just the metals. Now we're going to be discussing nonmetals. Some of the physical properties of nonmetals is that they're dull, they're not really interesting to look at. They're also brittle, which explains why they're not malleable or ductile. They have a low density, and because their particles aren't tightly packed together, they're not good conductors of sound. They can also be found in a solid, liquid, or gaseous state. Chemical properties. They are poor conductors of heat and electricity, which is why they're called insulators. They gain electrons in ionic bonds. They're also called anions. They have a high electronegativity and do not form alloys. They also have a low melting and boiling point. Their uses. Carbon can exist as either graphite or diamond. It makes up most life on the planet and reacts with oxygen to make CO2. We obviously need this substance, but it's very harmful. But plants convert it into oxygen, which is obviously what we need for respiration. Nitrogen makes up most of the air we breathe. It's around 78%, and it's used in nylon. How to locate them? They're found to the right of the semi-metals and to the right of the periodic table. So the semi-metals are just the orange ones. So all of the brown elements would be the non-metals. This red line is red's exact line is very important because it borders the metals and the non-metals. So the elements that come after the line would be considered non-metals. Semi-metals, a brief introduction. Semi-metals are also known as metalloids. They share some properties of metals and non-metals. They're shiny like metals but are very brittle. They are also semiconductors, which is why they're used in phones. They can form alloys with metals. They mostly behave like nonmetals, and boron, silicon, germanium, arsenic, antimony, tellurium are just some examples of them. Now we're going to be discussing the families of the periodic table. The alkali metals are just the group 1 metals. They're stored in oil and they're very active. The alkali earth metals are the group 2 elements. The transition metals are range from group 3 to 12. The halogens are group 17 elements, and the noble gases are group 18 elements. The charges of the elements. We can identify the charges of the elements by using this table. So group one would have a positive one charge because it's a metal. Group two would have a positive two charge. Group 13 would have a positive three charge, and because there are metals and non-metals in the column of group 14, it would have a positive four charge for metals and a negative four charge for non-metals. And group 15 metals having negative 3 charge, group 16 metals having negative 2 charge, group 17 metals having negative 1 charge. And because noble gases don't need to create chemical bonds, they don't have a they don't have a charge because they already have 8 electrons in their outer shell. But identifying transition metals is much harder. So you'll add the Roman numeral to in the brackets to make their charge predicted. So here iron would have a positive 3 charge.
Now, from our basic understanding on metals and nonmetals, we can now talk about ionic and covalent bonds. So what is an ionic bond? An ionic bond is a bond between one metal and one nonmetal. Their goal is to become stable by having both of the ions have a full outer shell to satisfy the octet rule. The octet rule is only applied to atoms, and it's a rule that states each atom have a full outer shell, which is around 8 valence electrons or more, depending on the element. Anyway, the metal ion donates an electron or more to the non-metal ion. The metal ion becomes a positively charged ion, and we call it a cation. It's positively charged because it loses an electron, which means that there's more proton than electrons. On the other hand, the non-metal receives the electron donated by the metal and becomes a negatively charged ion, and we call it an anion. The reason it becomes negatively charged because there's more electrons than protons. So anyway, this lets the ions to attract each other, the positive and negative, because the positive and negative attract each other, like magnets. So what is a covalent bond? A covalent bond occurs when an atom of the same element or close to each other on the periodic table share electrons. It only applies to nonmetals, so yeah. So the nonmetals can share more than one electron to satisfy the octet rule. The reason they do share is because they don't have the tendency to donate electrons, and for them the ionization energy is too large, and ionization energy means that the minimum amount of energy required to remove or donate a valence electron is too large for the covalent bond to have. So what's the properties of the ionic bond? The physical properties are that they have high melting and boiling points, they form crystals in solid state, they are hard and brittle, they are solid in room temperature, they conduct electricity in a molten state, not solid state, so when they're dissolved in a soluble, and they're mostly soluble in water. The chemical properties is they have higher enthalpies of fusion and vaporization compared to molecular compounds or paired compounds, and they have high strengths because of strong Columbus forces. So the higher enthalpies of fusion and vaporization means that the result from providing heat to a substance or providing heat to the ionic bond to change solid to liquid, so they can change solid to liquid or liquid to gas easily compared to covalent bonds. And the Columbus forces or Columbus law expresses the force through the non-moving charged particles in the ionic bond, track to moving of the atoms in the ionic bonds, attraction or repelling from one another. So what's the properties of the covalent bond? The covalent bond physical properties are they're soft, room temperature they're solid liquid gases, they have low melting and boiling points, they never conduct electricity, and they're often not soluble in water. The chemical properties are the structural isomerism, and they're only with metal, they're only non-metals, and their directional nature. Structure isomerism, like this here, mean that they have a molecular formula, like they can have different bonding patterns in atomic organization. So how do we present these two types of bonds? For ionic bond, we can use ionic lattice, dot and cross diagram, Lewis dot diagram, and the Borrow diagram. For covalent bond, we can use a dot and cross diagram, structural formula, a diagram, three-dimensional structures, Lewis dot diagram, and Borrow diagram. Okay, so here are like some pictures of the diagrams. So first up is the dot and cross structure for covalent bonds. You can see here that they're sharing electrons at two oxygen. The next one is a Borrow diagram in covalent bond. You can see here once again that they're sharing electrons to have a full outer shell of 8. The two chlorine gases. The next one is ionic bonding but with the Borrow diagram. And you can see here it's sodium and chloride, and like sodium donated electron to chloride, so they can have both of those two elements, ions, can have a full outer shell. And since here there's more electrons than protons, it became negative, and here there's more protons than electrons, so it became positive. So in here, lastly, is the Lewis structure for hydrogen, 2 hydrogen and 1 oxide. And you can see here that there's here the valence electrons shown, and here is the bonding between the two, like the sharing of electrons between hydrogen and oxygen. Okay, and that's going to be all for the diagrams. And the next slide here is how to identify the bonds. So covalent bonds are only bonds between two nonmetals. Binary covalent bonds are bonds like covalent bonds, but they have a prefix in the formula name. I'll show you soon. And the ionic bond are bonds between a metal and a nonmetal, or polyatomic ion compared. So that's going to be all. I'm going to be showing you how to draw, not how to draw, how to write the formulas and all of that in just 1 second.
Naming compounds. Alright, so the first thing we do is to first look at the element on the compound. If it's only nonmetals, then it's a covalent bond. If it's metal and non-metal, or if there's a polyatomic ion, then it's an ionic bond. But right now, we're just gonna do binary covalent compounds, which means that there's two different types of nonmetals. First, you write the name of the first nonmetal. Here, it's going to be carbon. And then we write the name of the second nonmetal. And here, it's going to be hydrogen. Alright, so here's the thing. In any bond, you always change the ending of the second element to IDE. So here it's going to be hydride. Not always, but like for now, we always change the second nonmetal to IDE in the ending. Next, you add prefixes. A prefix helps show the correct ratio of each element, and as right now a table will pop up to help you understand this more. So here there's 4 hydrogen, which means, and from the prefix table it's tetra. So we add here, it's going to be in the end carbon tetrahydride. Okay, and that's usually all you need to do for naming binary covalent bonds. But you do notice here, but there are some rules you need to know, that when you're using prefixes for binary covalent bonds, it's only for those type of compounds. And also, as you see, the prefix mono, which means there's only one of that element, isn't written in the beginning of the name of the formula, since it's just one of the rules. And another rule that you should know about prefixes is that when you have it with oxygen, you need to remove the O or A from it. For example, mono. Here, it's not going to be monoxide. It's going to be monoxide. You can see, like, we don't remove the O, or if there's an A, we remove the A. And that's going, and then here, so yeah, that's going to be all for this one. I'm going to be showing you another equation so you understand a bit more. And same thing, it's covalent compound, binary covalent compound. So the next compound is H2O. So what do we do first? Write the name of the first element, which is hydrogen. And we write the name of the second element, which is oxide. You can see here that I changed the ending to IDE. So now we look at our prefix table. How many of each element is present? Hydrogen has 2, while oxygen, when there's only 1. Since when there's no number, means there's going to be 1. So from the table, we know 1 means mono, so here's mono. And of course we put the O, because it's one of the rules. And for hydrogen, it's going to be dihydrogen, because there's 2 hydrogen, you see. And right now, the final equation, dihydrogen monoxide. Okay, now let's name ionic compounds. So from this formula, you can see that lithium is a metal and fluoride is a non-metal, and that's what the ionic compound is, a metal and a non-metal. So at the beginning we write, it's simple like a covalent, we write the name of the the metal, which is lithium, and then you write the name of the non-metal, which is fluoride. The same as a binary covalent bond, we change the ending to IDE and yeah, we add IDE to the root word. And we always write the metals first and the non-metals, since metals are positive because they lose an electron, and which means they have more protons than electron. And the non-metal is second because it's negative, so it's because it gained an electron, which means there's more protons than electrons. So in the end, the naming formula for LiF is lithium fluoride. And it doesn't matter if it's a metal or non-metal, it's the same with polyatomic ions. If the polyatomic ion is positive, then it's at the beginning. If it's negative, it's in the end. Now let's try an example with polyatomic ion. It's exactly the same. Here is NaOH. It's gonna right now pop up a polyatomic ion chart, so you know some polyatomic ion. There's many. But we're gonna right now just use this one. So we first name the first element, which is a metal, so it's at the beginning it's a positive one, so it's sodium. And then we write the polyatomic ion, which is hydroxide. And polyatomic ions in general, you don't change the ending at all, but this one is already changed, so we just leave it. But for other polyatomic ions like sulfate or nitrite or anything, you just leave the ending as it is. And that's going to be all for naming ionic compounds from a formula. Alright, now we're gonna be naming from the name of the compound to its formula. We'll start off with a binary covalent compound. So how do we know if it's binary covalent compound? We first look at the compound. If it has two non-metals, then it's a covalent compound. If it's a metal and non-metal, then it's an ionic compound, or if there's a polyatomic ion in there. So we know if it's binary if there's two different types of elements, but this is binary since there's two different types. So how do we actually have the formula from a name? So you right now look at this, the first non-metal, because we're doing binary, so it's non-metal, non-metal. We first look at the first element, and we look at the periodic table. It will pop up right now. Okay, anyway. So we look at the periodic table. We identify the actual element, shortened name. So here it's going to be I, for iodine. And then we look for heptafluoride. And we know hepta is a prefix because in binary covalent compound, there's always a prefix before the actual element. And so fluoride or fluorine is Fl, so here we write, F, so here we write F. And now, since we know that the prefix is hepta, which means there's 7 of fluoride, so we write down here 7, and here there's nothing in the beginning, which means there's only 1 of that element. So we don't write anything for that, and we leave it just like this. So in the end, iodine heptafluoride is IF7. And that's how you name a binary covalent compound, from its name to its formula. And you always remember, element, element, second element, second element. Look for prefixes and then add the prefixes to each element if necessary. And now we'll be talking about how we name from a name of an ionic compound to its formula. So once again, we first by checking each compound and by using the periodic table. If one of these elements is a metal and the other one is a non-metal or polyatomic ion, then you know it's an ionic compound. But for now, we're just going to do a metal and a non-metal. So you first write the symbol of the metal, and aluminum is Al, or Al. And then you write the name of the second element, which is sulfide. So here it's going to be S. And metal is always positive, since it's always loses an electron. So that's why it's always at first, because it's positive then negative, and non-metal are always negative because they gain the electron. Anyway, so now we wrote the actual element, but they also have charges. So we identify the charges by using the periodic table, and we already mentioned this at the beginning of the video. You can always go back and look at that. But we know from the periodic table that aluminum has a charge of 3 and sulfide has a charge of 2. Now, we're not done yet. We need to exchange the two charges so it can be balanced. And just a simple trick is to just change the two. So in the end, it's gonna be aluminum, so Al, 2, and sulfide S3. And just like this, we get an ionic compound name to its formula. Now, ionic compounds, but with polyatomic ions in the ionic compound name. So here it's barium, and here it's sulfate, and we can use our periodic table of elements to identify barium, which is Ba, and from our polyatomic ion chart, which was shown a few minutes ago, you can check back, or you can search online. either your choice. A sulfate is SO4. And now we need to identify the charges from our periodic table and from the polyatomic chart. Where barium is +2, because it's a metal, and sulfate is -2. Alright, so here's the thing. If both the charges are exactly the same, like +2 and -2, then they technically cross out because both of the charges are equal. So in the end, it's just gonna be BaSO4, and that's how you name a polyatomic ion formula from the name of the compound, ionic compound. Lastly, we'll be naming ionic compounds, the name, with a transition metal. And since transition metals are a bit the charges are a bit hard to identify, we always figure out the charges by using their Roman numerals beside the transition metals element, like here. So how do we name this element? So we first find 10, the element, which is as SN, sorry. And then the same for chloride, which is Cl. And then we write down the charge for each. So here's 2, and chloride is -1. So here's +2, because metals, positive, all metals, negative, they're always next after the metals. And then, as our trick was shown, switch the two elements. Switch the two charges so it's balanced. And then the end it is SnCl2. The 2 went for the chloride, the -1 went to 10, and the 2 got it from here. So in the end it's this. So 10 here is like this as a formula. And that's going to be all for naming ionic and covalent compounds and writing down their formulas from the name and opposite way around. Now we're off to chemical equations.
Now we're going to discuss why we balance equations. We balance chemical equations because to follow the law of conservation of mass, it's when the mass of the reactant needs to be equal to the mass of the product. This is just a simple example. So here we have N2 plus H2 yields NH3. So these are the reactants, these are the products. This is just the one of the products. So you can start by determining how many atoms of nitrogen and hydrogen there are in the reactants and how many there are in the product. So here N has 2, H has 2, N has 1, H has 3. And now we're obviously going to need to balance this. To make the nitrogens balanced, we're going to have to add a coefficient of 2 there. Now the nitrogens are balanced. But now we see that the hydrogens aren't balanced because there's a 6 there. To make them equal, you're going to have to add a coefficient of 3 here. So this would be the final balanced chemical equation. Parts of the balanced chemical equation. So we have the reactants, products, elements, subscript, and the coefficient. These are all the reactants, these are all the products. The letters in inside the brackets are just the states. So this one would be solid, this would be liquid, this would be gas. The element or the compound is just called the formula unit. The whole number that comes in front of the formula unit is the coefficient. And the small number that comes after the element is called the subscript. It cannot ever be changed. Because it will change the whole formation of the equation. To identify a balanced chemical equation, check if the number of atoms in the elements in the reactants are equal to the product. Now we're going to be discussing the types of chemical equations. So synthesis reactions are fairly simple to recognize. They are when the reactants directly combine with each other to form one product. There can be more than one reactant, so you can recognize them by thinking that they're the opposite of a decomposition reaction. They can include polyatomic ions too. So to make it more easy to recognize, just use the form A plus B yields AB, which is easier to find because there are two specific reactants that form one complex product. So here, Fe would be the A, S would be the B, and FeS would be the AB. This is just another example. Decomposition. Decomposition can be thought of as the opposite of synthesis reaction. It's when one reactant produces two or more products. It is easily recognized because you just have to look for one reactant that is broken down into two or more products. It's usually written in the form AB yields A plus B. This always makes it so much easier to understand. So for example, here the H2O would be the AB, and which yields H2 plus O2. So the H2 would be the A and the O2 would be the B. Single displacement. A single displacement reaction is when the first reactant is swapped or exchanged with the ion of the second reactant. They're usually written in the form A plus BC yields B plus AC. So here, an example of this is Fe2O3 plus 3C yields Fe plus CO2. So you can think of FeO as the BC and the C as the A. So here it will yield. So here the iron would be the B and the CO2 will be the AC. Just always remember this form. Single displacement. A double displacement. A double displacement reaction takes place when two reactants swap ions to form two new products. You can tell if it's a double displacement if the cation swapped with the anion. They are written in the form AB plus CD yields AD plus CD. There are two main types of double displacement reactions, and they are precipitation and neutralization. Precipitation is when two liquids create a solid, and neutralization are between an acid and a base. A salt is produced if the solvent is water. So here an example of a double displacement reaction would be BaCl plus NaSO4. So this is a polyatomic ion. Yields BaSO4 plus 2 NaCl. BaCl would be the AB. NaSO4 would be the CD. BaSO4 would be the AD. And the NaCl would be the CB. This is just another example. Combustion. So this is just the fire triangle. We need fire in a combustion reaction because a combustion reaction is just a type of chemical reaction that can be referred to as burning. So the fire is just has to have oxygen, heat, and fuel. The usual formation of a combustion reaction is hydrocarbon plus oxygen yields carbon dioxide plus water. You know that you have a combustion reaction if one of the reactants is oxygen and the products is carbon dioxide plus water plus heat. An example of this is the combustion of methane. So SH plus O2 yields CO2 plus H2O. You know that it's a combustion reaction because oxygen is one of the reactants and CO2 plus H2O is one of the are the products. Complete and incomplete combustion. Complete combustion is when the products are only carbon dioxide and water. It's also known as clean combustion. Meanwhile, incomplete combustion is when the products include carbon monoxide and/or carbon and carbon dioxide. It's also known as dirty combustion. If you didn't already know, many fossil fuels burn with incomplete combustion, and it's really, really harmful for the environment and for the body. Thank you for listening. I hope you understand the basics of chemistry in more depth.